Hello, everyone. Welcome again for another brief session on using simulations for power electronic simulation and generally on Simulink topics here. You can apply these concepts to any other simulation application. You have to think carefully, when you do these simulations. So I want to provide you some tools, some explanations on how to use Simulink and how it works, basically. Okay, so these are some fundamental concepts. Now, when you set up a simulation, whether it's a sim power simulation or your regular transfer function based models that you use, you have to think of it as a numerically executed model. What that means is essentially MATLAB basically works with matrices, right? So when you set up a differential equation, those differential equations, differential equations are essentially your transfer functions, right? When MATLAB solves those transfer functions, essentially it solves it through numerical methods. Okay, meaning they will have some form of an algorithm trying to see if it's optimized, if it's reached a steady state point in a numerical fashion rather than your closed form expressions that you have for differential equations. Okay, that means it's trying to see if a value has reached a certain threshold, certain accuracy in real time or pseudo real time at the using your CPU clock or CPU power. Okay. Now, when we run simulations, we have to be a little smart when we set up certain algorithms or simulations, or when we get errors, especially when we get errors. All right. Now, if you recall from our previous discussion, we looked at how to set up the simulation for the RLC simulation or RLC board simulation or other labs in the past. Okay, so I instructed you to use fixed step ODE4 and the step size as 1e minus 5, and we ran it for 0 to 2 seconds. Now today when you try to run this same simulation with a buck converter, right, and we need to update the PWM generator to be at 100 kilohertz, right, 100 kilohertz, and we say if we try to run this, we have to understand that this may not work. That should be the intuitive knowledge you should have, because see, we have a much larger step size, right? We are asking the simulation to execute at this step size, and then we want information to generate from the PWM generator at a much faster rate, which is not practical. Okay, so if you try to run this simulation, it's gonna throw out an error. Okay, I'm going to show you the error. So it's saying invalid setting for fixed step size 1e minus 5. All sample times in your model must be an integer multiple of the fixed step size. Okay, so that means we have somewhere in our simulation, we have a fraction of a step size or a non-integer multiple of my step size, which is true, right? Which is true because our step size is 1e minus 5, and then our sampling period is what is it there? Is that 1e minus 1, 2, 3, 4, 5. So that means it's matching, it's the same, and then the differential equations cannot be solved unless you run the simulation faster. So essentially, if you have a certain frequency in your Simulink model, you have to run the simulation much faster, typically 1,000 times faster or 100 times faster. All right. especially when you run fixed step. All right. So since we want our Simulink model to run at 1e minus 5 period, or this PWM frequency is at 100 kilohertz, right? That means 1e minus 5 period. We need to have more data points within that 1 PWM interval. Therefore, what we're going to do is we're going to go back here and say, hey, since we are running fixed step, we're going to make this step size much smaller. Okay, so 1e minus 8. 1e minus 8. Okay, and we say, okay, now before we do that, now we have to remember, we're going to run it at this very finer step size for 2 seconds, right? So that means we're going to have a long number of data points, a large number of samples, and it's going to take a very, very long time. So what we can do is, to avoid this, we can actually reduce this runtime, so that our simulation will run. Okay, let's try 0.01. Okay, so we can set that, and then we can save our model, and let's run this. Okay, so now it's not giving us any error because our simulation run time is much faster than our PWM frequency. Okay, so we have the model running. Okay, so let's take a look at our results. So when we look at our results, we can see that we have a transient, and then it's kind of settling in, but not fully settled. So we have to again be a little cautious here. We have to make sure we run it long enough so that the model has reached steady state. Okay, it has to reach steady state. So let's extend this time. Let's extend this time to 0.05. 0.05, and let's see if that helps us. Okay, and yeah, see, longer the time we run, you can see the longer the simulation time, the longer the simulation takes to run. Okay, so if you have 2 seconds, it might take like maybe half a day, or depending on your computer, it might take even longer. So be careful of what you choose here. Okay, so give it a second here, and you can even monitor these waveforms real time if you want. Yeah, see, you can now see the waveforms settling in, right? They're settling in to a steady state. Okay, so that this is good. This means it's working, right? It's working, and this is what I'm expecting you to do. Now, in this way, I showed you how to use the fixed step size. Fixed step size approach works most of the time. I'd say 95 or 98% of the time. But another very quick and easy way to see if your simulation will run is go back to your simulation configuration, the model configuration. Instead of running it at fixed step, you can easily choose variable step. Okay, so now when you choose variable step, there are much more settings that you have here. Okay, this is the settings dictate how the differential equations are solved, how the optimization algorithms are run. Okay, and I'm not going to go into those details right now. Feel free to read up on those settings, through MATLAB documentation. But easily, by choosing variable step and automatic solver selection, you can actually test out if your simulation runs the first time around. Okay, so you can run that, and it sometimes it runs faster, sometimes it takes longer. Okay, and now you can see you got almost the same result, and it even ran a little faster, and you can see all the details. Okay, so this is with variable step configuration. So use those two key modes of simulation, and don't try to run a simulation blindly. Try to see uh, try to understand, are my settings correct to run this simulation? Is there anything that is out of place that might throw off an error? Or when you get an error, try to understand what that error is telling you. Okay, and then you can solve the problem that you are seeing. Okay, all right. So hopefully, this helped understand some of the concepts behind Simulink and using simulation for your lab classes. Okay, thank you.